Hey class, today I will be teaching you about array operations, specifically insertion, deletion, update, and search, and why you should care about them. This video requires knowledge of array properties and Big O notation. If you are unfamiliar with these topics, I have videos on both of these topics that I'll link in the description. We're going to start off with a quick review of arrays. Recall that an array is a data structure that can store collections of items. Arrays have the following properties: contiguous memory allocation, order, homogeneity, and random access. One important feature of arrays is that we can iterate over them. Here's an example of some code that iterates over the array of my favorite booleans. I know we went through that review kind of fast. If you'd like to go over arrays more in depth, feel free to watch my previous video or leave a question in the comments. The first operation we will talk about is insertion at the end. Our goal here will be to insert the number 1 at the end of the array. There are two scenarios. Scenario 1 is that we know the index of the first available spot. In that case, we can simply access it and then insert our element. Remember that random access means we can do this in constant time, so in this scenario, insertion at the end has O of 1 time complexity. In the second scenario, we don't know the index of the first available spot. That means we have to go through the entire array until we find the empty spot. Then we access it and insert our element. Searching for the empty spot means that we have to go through the whole array, so that is O of n with respect to n elements of the array. Then the actual insertion itself is O of 1, so overall the time complexity is O of n. Next, let's talk about insertion at a specific index. Our goal here is to insert the number 4 at index 1 in the array. However, we can see that index 1 is currently occupied by another number, which means we will first have to shift all of the elements from index 1 onwards one space to the right, like so. Now that the spot at index 1 is empty, we can insert the number 4. Then, it takes O of n time to shift the array elements, and O of 1 time to insert once the index is freed. So overall, insertion at an index has O of n time complexity. The next operation we will look at is deletion. Here, our goal is to delete the last element of the array. Assuming the array is full, we can simply access the last element of the array and then delete it. Then, deletion from the end has O of 1 time complexity. Next, let's look at deletion at a specific index of the array. Here, we would like to delete the element at index 1. First, we access the element at index 1, and then we delete it. However, now we have a gap in our array, and we need to close it to preserve the array property of contiguous memory. So, similar to what we did for insertion at an index, we're now going to shift each element after index 1 to the left, like so. Deleting the element at a particular index is O of 1, and if we delete the first element, we will have to shift the entire array, so shifting elements is O of n. Then, deletion at an index has O of n time complexity. Next, let's talk about updating the element at a particular index. Here we wish to update the element at index 3 to be 4 instead of 1. Updating is pretty simple. We just select the element at index 3 and change its value. Due to the random access property of arrays, this has O of 1 time complexity. Lastly, let's talk about searching an array using linear search. Here I have an array of cat names and I want to find the index of the name Simba if it exists in the array. To do this, I iterate over the array until I find Simba. If Simba is not in the array, then I will have to go through the entire array before confirming that Simba is not present. Then, as the name suggests, linear search of an array has O of n time complexity. I want to point out that this search method is specifically a linear search method that can work on both unsorted and sorted arrays. If we have a sorted array, we can use something called binary search, which will be much faster. I won't get into the details in this video, but it is worth mentioning. So, why care about array operations? I mentioned in my previous video that arrays are useful for modeling things we encounter in our everyday lives, such as a shopping list, a closet, or a chessboard. Array operations are what allow us to have such good representations of these objects. For example, array insertion and deletion can help us add new items to our shopping list or cross off items that we have already bought. I also mentioned in my previous video that arrays are the building blocks of many other data structures, such as heaps, hash tables, stacks, and queues. If we couldn't insert, delete, update elements, and search for elements in arrays, these data structures would not be able to function. Let's summarize what we've learned today. First, we learned that insertion at the end takes either O of 1 time if we know where the first empty spot in the array is, or O of n time if we have to look for it. We learned that deletion at a specific index takes O of n time because we have to first shift all the elements at that index or greater to the right, and then insert. Then we learned that deletion at the end, assuming a full array, takes O of 1 time, and deletion at an index takes O of n time because we have to first delete the element at that index and then shift all of the following elements to the left in order to close the gap. Then, we learned that updating an element at an index takes O of 1 time. Next, We learned that we can search for an element in an array by iterating through every element. This is called linear search and takes O of n time. Lastly, we learned that we should care about array operations because they are what make arrays such good models of physical objects and are also what allow arrays to be the foundation for more complex data structures. Thank you so much for watching, and please, feel free to comment any questions you have about the video or any topics you would like me to cover next. I also welcome feedback for how I can improve my videos. As always, this is your CS Professor of Fun.